This next topic, Thermochemistry 2, special delta H's and Hess's law, is probably the most important generally of all the sections in thermochemistry. It's one that gives rise to some of the more fun problems, and it's also one that gives rise to some of the more challenging problems. So I'm going to take the questions that were on the worksheet and I'm going to split this work through into three distinct types. Okay, the first type is going to be just thinking about special delta H's, bringing in some of that molar quantity. The next section is going to be the questions where you have to build up delta H for a particular equation by building up that equation from some equations you were given. It's a weird permutated way to say things, but if you know the questions, you know the kind of meaning. And then Hess's law, finally, what it means to most A-level students, the idea that delta H of the reaction is where you sum the delta H of formation of the products, sum the delta H of formation of the reactants, and subtract the reactants from the products. First two questions associated with, do you know the definition of the heat of formation, delta FH? In this case, we're looking at copper sulfate. So the heat of formation for copper sulfate, heat of formation for anything, is when you make 1 mole of that substance. Well, all our possible answers here are making 1 mole of copper sulfate. But it's not enough just to make 1 mole of copper sulfate. You have to make it from the elements in their natural or standard state. So when we look at CuSO4, the natural state of Cu is a solid. Natural state of oxygen is diatomic gaseous molecules, O2 gas. Natural state of sulfur should actually be S8, nice solid with molecular solid in which those molecules are puckered rings of 8 sulfur atoms. However, just to make it a little bit less yucky, I just put in solid sulfur. So the only possible answer is that first one, where you got the elements there, copper solid, sulfur solid, and 2O2 gas. Second possible answer did indeed have an element, but it reacted the element with a compound. Next one are 2 compounds reacting together. The next one, 2 aqueous ions coming together to make a precipitate copper sulfate. And then the last one, just again precipitating copper sulfate, in this case from its aqueous solution. Actually, that and that are the same thing, just written out slightly differently, because of course copper sulfate is an ionic compound, so it dissociates. But anyway, that's just by the by, because the answer is this one, making 1 mole from the elements in their natural state. Question 5, which of the following substances is the standard enthalpy of formation not 0? Under standard conditions, or the standard enthalpy of formation, as we just said, is making 1 mole of a substance from its element in their natural state. And as we look down this list here, mercury liquid has its natural state. Water isn't even an element, so that looks like a pretty good one for the answer. Sodium is an element and natural state is solid. Hydrogen is an element, natural state diatomic gas, H2 gas. And iron is an element, natural state solid. So the only one of those that wasn't even an element was water. And we didn't even have to get so much into the natural state argument, although that is the natural standard state for all of those 5 elements. Now we'll bring together our definition of heat of formation that we had previously with the molar concept of delta H that we discussed before. So this equation right here is saying let's take 2 moles of Fe2O3 and turn it to 4 moles of iron and 3 moles of O2. And when we do that, the heat of formation for 2 moles going to 4 moles plus 3 moles is 1,644. Okay, so that's what that equation is telling us in terms of moles. We're looking for the standard heat of formation of Fe2O3, and of course standard enthalpy of formation, as we've seen now 3 times, is where you make 1 mole from an element in its natural state. So we'll take our equation as written with pretty colors, for which we're told the heat is 1,644. But this has Fe2O3 on the wrong side. We don't want it on the left, we want to make it. So therefore, let's flip the equation around to now where we've got Fe, 4Fe plus 3O2 goes to 2Fe2O3. As we flipped the equation delta H flips, so now instead of being plus 1644, it's now minus 1644. I actually just want 1 mole of Fe2O3. So what I'll have to do there is take this equation, which does indeed have the elements, but twice as much of them as we need, so divide it by 2. So now instead of 4 I've got 2, instead of 3 I've got 3 halves O2, and instead of 2 moles of Fe2O3 I have 1 mole of Fe2O3. And of course when I halve the coefficients I have to halve delta H. Minus 1644 halved is minus 822. Same idea really for question 7. Okay, except now I'm moving off heat of formation and moving into heats of combustion, right? So delta COM H instead of delta FH. So during an experiment, 10 grams ethanol release, blah, blah, blah. Okay, during the combustion, 296 kilojoules of heat energy is released. Of course, that's minus. So when I got 10 grams of ethanol, it's 296.6 kilojoules released. I'm interested in what happens when I burn 1 mole of ethanol. Well, 1 mole of ethanol is 46 grams per mole. As we said here, this heat energy is released, which means delta H is negative. So I'm setting up a little ratio, as I did back in the first set of questions. I know that 10 grams corresponds to minus 296.6. I'm interested in what's the heat that corresponds to 46. So set it up as a little ratio, multiply it out, and we find that the heat of combustion minus 1,362 kilojoules per mole. So this is a molar heat question, but for which you need to know the definition of heat or enthalpy of combustion. So question 8, a question I find particularly appealing, one that tests an awful lot of concepts. I'm giving you a couple of equations. Let's make it nice and pretty here. Okay, so NO gas goes to half N2 plus half O2, and I'm saying that the heat of that equation, so the heat change when 1 mole of NO turns into half a mole of N2, half a mole of O2, is delta H1. And when 2 moles of NO turns into 1 mole of N2O and half a mole of O2, well, the heat for that is delta H2. And now I'm going to set up various relationships and test them. So the first one was, does the heat of formation for NO gas equal delta H1? In other words, does the equation that corresponds to the heat of formation for NO correspond to this equation up here? Well, when you have a heat of formation, you're making 1 mole of a substance, or making 1 mole of NO from its elements in the natural state. Well, nitrogen's element natural state half N2 or N2, oxygen's element natural state O2. To balance it, to get 1 mole, you can only have half a mole of N2, half a mole of O2. Well, that is not this equation here for delta H1. So therefore, delta H1 is not the heat of formation for NO. Now, those who want to take it a little further will notice that, of course, actually, this equation is the flip. So the heat of formation of NO equals minus delta H1, because to get this heat of formation equation, flip this first equation. If I flip an equation, I change the sign of delta H. How about moving on to the delta H2 equation? 2NO goes to N2O plus a half O2. Well, the delta HF for N2O will be again making 1 mole of N2O from its elements in a natural state, N2 and O2. In this case, I've got 2 nitrogen atoms in my final molecule, so that's fine, N2. I've only got 1 oxygen atom, so it'll be a half O2. This is very definitely not this equation here. So not even close does the delta H2 correspond to delta HF for N2O. How about delta H2 is 2 times delta H1? Well, 2 times delta H1 is just 2NO goes to a whole N2 and a whole O2, okay? And the equation for that, or the heat for that, would be twice delta H1. Does that equal delta H2's equation? No, you've got the 2 NOs, fine, but then instead of it being N2 plus O2, we've got NO2 plus a half O2. So thus, twice the delta H1 does not equal delta H2. Now this one here, let's get really muddled and confusing, shall we? We said delta H1 we did NO goes to half N2 plus half O2. So twice delta H1 here is 2NO goes to N2 plus O2. So minus 2 delta H1. Change the sign on delta H, flip the equation. So now it becomes, instead of 2NO to N2 and O2, it becomes N2 and O2, goes to 2NO. Hope you're paying attention to all those 2's and N's and O's. And then we got delta H2. Well, delta H2's equation is just the 2NO goes to N2O plus a half O2. Now let's add those together to get the delta H2 minus 2 delta H. And as we add them together, the 2NO's will cancel out. Half of the O2 on the right cancels out with a half O2 on the left, leaving a half O2 on the left behind. And we get this nice little equation here. Okay, make sure that you see how I got there. So delta H2 was this. I doubled delta H1 and then turned it to a minus sign and then put those together to get N2 plus half O2 goes to N2O. And look at that. That looks remarkably like the heat of formation for N2O. N2 plus half O2 goes to N2O. So indeed, that is correct, that when we take the equation that corresponds to delta H2 and subtract from it twice the equation that corresponds to delta H1, we do indeed get N2O formation equation. And then, of course, finally, delta H1 equals delta H2, not even close. So Cute One tested all kinds of fun little concepts and relationships.